Let's talk about complex zeros of polynomials. In a previous video, we reviewed complex numbers, how to add, subtract, multiply, divide them, talked about the complex conjugate, and now we're going to apply all of that complex number knowledge to polynomials. Let's start by looking at the polynomial x squared plus 9. We're asked to find all the zeros, then write the polynomial as a product of linear factors. To find the zeros of a polynomial in general, you're setting the polynomial equal to 0 and solving for x. Previously, x squared plus 9 was not something we could solve. It's called a sum of squares, and it was unfactorable. But when we're given the breadth of the complex numbers, we actually can factor this. So I'm going to subtract 9 on both sides and get x squared equal to -9. Remember, the square root principle says that if x squared is equal to a number, then x is equal to plus or minus the square root of that number. It's the same idea as taking the square root on both sides, but you add in a plus or minus if you do that. So x squared is equal to -9 gives us x equal to plus or minus the square root of -9. X is equal to plus or minus I square root 9. X is equal to plus or minus 3i. These are the zeros of the polynomial x squared plus 9. The way that we write polynomials as products of their linear factors, we write the polynomial as x minus the 0. And you do that for as many factors as you have. So it's x minus the 0, x minus the 0. So if we have two zeros, if we have 3i and let's write this as let's write it as -3i, comma 3i. Those are our two zeros. That means f of x can be written as x minus -3i and x minus 3i. That gives us x plus 3i times x minus 3i. Boom. Just like that. And if you were to FOIL this guy out, you would see you have x squared minus 3ix plus 3ix minus 9i squared. Those middle terms are going to cancel. You're going to get -9 times -1, which is x squared plus 9. So it all works out. Let's look at another one. This says to use the quadratic formula to find the zeros of the following polynomial, then write the polynomial as a product of linear factors. So we're told to use the quadratic formula here. We should. We know the quadratic formula is x equals -b plus or minus square root b squared minus 4ac all over 2a. In this case, a is 1, b is 6, and c is 18. So if x equals -b, -6, plus or minus b squared, so that'll be 6 squared, minus 4 times a is 1, c is 18, all over 2 times 1, which is a. Simplifying, we have -6 plus or minus 36 minus 4 times 18, 72. Well, you know what? I'm grabbing my calculator, making sure. 72, good job. Good job, me. Minus 72 all over 2. This is -6 plus or minus the square root of -36 all over 2. The square root of -36 is going to be 6i. -6 plus or minus 6i divided by 2. If you divide everything in the numerator by 2, you get -3 plus or minus 3i as your zeros of the polynomial. So the zeros, one of them is -3 plus 3i. The other one is -3 minus 3i. So two zeros. The way that we write our polynomials as a product of linear factors, again, it's always x minus the 0. So our polynomial g of x would be x minus literally this entire thing. That's one factor. Times x minus, I'll put parentheses again, the other. And that's literally your final answer. Even if your answer ended up messier with radicals and stuff, it wouldn't matter. It would still, with anyone where you have imaginary roots or zeros, you're going to have something that looks messy like this. The mistake I see people making, the plus or minus changes because of the quadratic formula. The quadratic formula has a plus or minus in it, right? So the only pluses and minuses that get changed were these guys here, and they came from this original plus or minus. It's all the way back here. I see students changing these guys here, but it's always x minus the 0, x minus the 0. So you're never having an x plus here. Unless, of course, you've simplified something like x minus -7, in which case that is x plus 7. But in the case of the complex conjugate, which is not this case here, it's going to just look messy. All right. Let's do another problem. For the polynomial below, 2 is a 0. Express g of x as a product of linear factors. We had a problem very similar to this in a previous video. I think in the factor theorem video, we did a problem similar to this. Let's go ahead and work through it. So if 2 is a 0, that's going to mean that g of x can be written as x minus 2 times something. This something right here is going to be the result of dividing g of x by x minus 2. This is the quotient obtained by dividing g of x by x minus 2. So if you divide g of x by x minus 2, you'll be left with a quotient. That quotient comes here. G of x will factor into these two things. This is going to end up needing to be factored further. We'll get to it. So doing synthetic division, we're doing g of x, which is x cubed minus 8x squared plus 19x minus 14, all divided by x minus 2. Synthetic division tells us, hey, take the opposite sign. And we're able to do synthetic division here, by the way. We're able to do synthetic division here because this is of the form x minus a number. The divisor is of the form x minus a number or x plus a number. I'm taking my coefficients, putting them in. If this looks very foreign to you, please go watch my video on, the factor theorem, but also synthetic division and the remainder theorem. Also, complex numbers will be useful. Please go watch all previous videos. Pull down the 1. 1 times 2 is 2. -8 plus 2 is -6. 2 times -6 is -12. 19 minus 12 is 7. 7 times 2 is 14. -14 plus 14 is 0. This all checks out. That was what was supposed to happen. We have a remainder of 0, which is what should happen if x minus 2 is a factor. So this leftover stuff here, that's from this. This is the quotient that's left over. So the quotient is x squared minus 6x plus 7. We were told to express g of x as a product of linear factors, and if we left our answer like this, it wouldn't be correct because this is not a linear factor. We have to factor x squared minus 6x plus 7. Now, if you try to factor this using your typical factoring methods, it's not going to turn out. You're going to have to use the quadratic formula on it. The quadratic formula, again, just group that, bring it on down with me. Come on down. I like to have it on the screen so students can look at it. There you go. So factoring x squared minus 6x plus 7, you get x equal, let me write down my ABCs. A is 1, B is -6, C is 7. X is equal to negative B, sorry, not negative, -6, plus or minus the square root of -6 squared, B squared, minus 4 times A times C, all over 2A. You know, this is looking like it's not going to come out to be complex. That's a little frustrating. Give me a moment. Let me pause this video. All right, this problem was supposed to come out to have, at least I had chosen this problem because my intention was to have a complex answer. It's not going to come out to be a complex answer, but I'm just going to finish this example. We're already here. I want to go spend Sunday with my son. I'm finishing this video. I have run into enough problems today. Pretend there's imaginary numbers. The only difference is going to be that there's an I involved. Going forward, I'm just moving forward with this example. 6 plus or minus the square root of 36 minus 28 all over 2. This here is going to be the square root. The square root of 36 minus 28 is going to be the square root of 8. And the square root of 8 simplifies down to the square root of 4 times the square root of 2, i.e. 2 square root of 2. So we get 6 plus or minus 2 square root 2 all over 2. And that simplifies to 6 plus or minus, not 6. This simplifies because everything is divisible by 2. 6 divided by 2 is 3. 3 plus or minus the square root of 2. Those are the other zeros. So 2 is a 0, and the other 2 zeros are 3 plus the square root of 2 and 3 minus the square root of 2. So all the zeros together of this polynomial are 2, 3 plus square root 2, 3 minus square root 2. So writing g of x as a product of linear factors, x minus the 0, x minus 2, x minus this, 3 plus square root 2, but in parentheses, x minus 3 minus square root 2 in parentheses. Again, my intention was that this would come out to be an imaginary number. If it did, if this came out to be an imaginary number and you had like an eye on it, this whole process would look the same. It would look just as nasty, except for there'd be eyes on these. So there's that. There's that problem. That's the second time this has happened to me today on these videos. Okay. The conjugate zeros theorem, let's talk about that. So if a polynomial has a plus bi as a root, then the complex conjugate a minus bi is also a root of that polynomial, i.e. complex roots always come in pairs. Always come in pairs. Notice that happened up here, the zeros. Well, they weren't complex in this case. They were supposed to be, so I could say, look up here. But I guess that just didn't work out for me. Man. So let's just go ahead and do some more problems. Find a polynomial of degree 3 with real coefficients and the following zeros. -3, 2 plus I. Here's a fun fact. The degree of a polynomial is the number of zeros that polynomial has. If a 0 is repeated, then that counts as a 0. So essentially, if you have factored into linear factors, if you have a polynomial written as a product of linear factors, the number of linear factors is the degree of the polynomial. So our zeros that they told us we had are -3, 2 plus I, and the conjugate zeros theorem says that the complex conjugate 2 minus I must also be a 0. When we write this in factored form, this becomes x minus -3. This becomes x minus 2 plus I. This one becomes x minus 2 minus I. So f of x is equal to x plus 3. I'm going to leave these guys in their form they're in, but I am simplifying the plus 3. And that's that. We were told 2 of the zeros, then we use the complex conjugate to find the next one. Then you just have to write it as a, well, you know what? I actually think this problem on Alex makes you multiply it out. So if it makes you multiply it out, why don't we multiply it out? Let's multiply it out, just for fun. Pause the recording, hold on. All right, so in my review of complex numbers video, I talked about multiplying out expressions with complex numbers in them. I'm going to start by multiplying this guy out. So I'm going to multiply x, and then that means I will want to distribute the negative. If I'm doing it the full way, if I'm multiplying it all the way out, let's do it the full way. So distribute that negative. X minus 2 minus I multiplied by x minus 2 plus I. We are multiplying this out and we're using box method. If you want to hear more about that, look at the complex number review video. So I'm going to take this guy, I'm going to put him on top. We have x minus 2 minus I. And I'm taking this guy and putting him over here. So we have x minus 2 plus I. We have x squared minus 2x minus ix minus 2x plus 4 plus 2i ix negative 2i and negative I squared. Negative I squared. So negative I squared, that's negative 1. Negative I squared is just 1. We can look diagonally to simplify this. So we'll still have this x plus 3 we have to deal with, but simplifying, we have x squared negative 2x minus 2x is minus 4x. We have positive ix and negative ix, those will cancel. Negative 2i, positive 2i, those will cancel. We don't have I squared anymore, we have 1, so we have 4 plus 1 is 5. What's left is for us to multiply these guys out. So we have one more multiplication, and you can use box method again. I can move this guy, down here, goodbye. Where's that 1 from? Oh. Go ahead and move down there. I'm gonna multiply these guys together with box method as well, and I am feeling very lazy. So this is gonna be, I have run into some technology issues today. Feels like this semester just like has it out for me as far as technology issues go. All right, x squared minus 4x plus 5 goes up here. X squared minus 4x plus 5. And then x plus 3 will go on this side. So I'm multiplying together these two. You don't have to use box multiplication. It just makes everything way easier if you do. Up to you. So we have x cubed minus 4x squared, 5x. Then we have 3x squared minus 12x plus 15. Combining together are like terms. We have an x cubed. We have 3x squared minus 4x squared, so negative x squared. Negative 12x plus 5x is minus 7x. And then 15. So this polynomial, x cubed minus x squared minus 7x plus 15, has these zeros. If you're doing this problem on Alex, just double check what the requirements are. If they don't want any complex numbers in their answer, then you can't give your answer like this. You're going to have to go at least a step further, but probably all the way down to this step here. This is an acceptable answer. This is the right answer. It's just potentially not in the right form, which is why we multiplied it out. Okay. So this I think this is our last problem here. So find all the other zeros of p of x equals x cubed minus 4x squared plus 6x minus 4, given that 1 minus I is a 0. So we have that 1 minus I is a 0. And the complex conjugate theorem says if that's true, then 1 plus I must be a 0. So we know that this polynomial at least factors into x minus 1 minus I times x minus 1 plus I. And then there should be one other factor. It's a cubed polynomial. It's a degree 3, so there should be 3 linear factors. So there's one other factor here, and we really want to figure out what that is. The best way to do that is going to unfortunately be for us to multiply out this right here and then divide the original polynomial by this new quadratic factor. These two will multiply together to create a quadratic factor. I can divide this polynomial by my quadratic factor. And what I'll be left with is this remaining factor. So let's put it down here. Distributing the negatives. We have x plus 1. Oops, sorry. X minus 1 plus I times x minus 1 minus I. Okay, I'm going messy this time. I don't have patience. All right, so I'm putting this polynomial on top. X minus 1 plus I, putting this polynomial on the side. X minus 1 minus I. We have x squared minus x plus ix minus x plus 1 minus I minus ix plus I minus I squared. Negative I squared, by the way, that's going to be negative 1. That's positive 1. So negative I squared is just positive 1. So this comes out to x squared. Negative x minus x is minus 2x. Negative ix and ix cancel. I and I cancel. Then we have 1 plus 1, which is 2. Again, to find this remaining factor right here, we're going to need to divide this guy by x squared minus 2x plus 2 using polynomial long division. So x squared minus 2x plus 2 divided by, well, not divided by, dividing x cubed minus 4x squared plus 6x minus 4. So x cubed divided by x squared is x. I'm going to be doing this a lot faster than I did my division video. I'm doing a little bit of steps in my head. I'm just going to trust that you understand it. If you don't, go back to the polynomial long division video. This will be minus x cubed plus 2x squared minus 2x. Negative 2x squared plus 4x minus 4. Negative 2x squared divided by x squared is negative 2. So we're going to get plus 2x squared minus 4x minus 4 or plus 4. Remainder of 0, which is exactly what we were hoping for. So this mysterious factor here is x minus 2. Mysterious leftover factor. Now, this question said to find all the other zeros. So I have factored it, but I haven't found the other 0. The other 0 is obtained because x minus 2 is a factor, means x equal to 2 is a 0. So our zeros are 1 minus I, 1 plus I, and positive 2. All right, my friends, that is all then I have for you. That is the end of that worksheet. We're done. I hope you have a great day. I hope your technology works. I'll see you in another video. Bye.